Massive sulfide deposits. Massive sulfide deposits, often referred to as volcanogenic massive sulfide deposits, are significant sources of various metals, including copper, zinc, lead, gold, and silver. They form on or near the seafloor through volcanic and hydrothermal processes. Here's an overview of their formation, characteristics, and economic importance. Formation. Tectonic setting. Volcanogenic massive sulfide deposits typically form in extensional tectonic environments, such as mid-ocean ridges, back-arc basins, and island arcs, where volcanic activity is prevalent. Hydrothermal activity. Seawater infiltrates the oceanic crust through fractures and is heated by underlying magma. This heated water leaches metals from the surrounding rocks. Metal precipitation. As the metal-rich hydrothermal fluids rise and mix with cold seawater, the metals precipitate out, forming massive sulfide deposits on or just below the seafloor. Characteristics. Ore composition. Volcanogenic massive sulfide deposits usually contain high concentrations of sulfide minerals such as pyrite, chalcopyrite, sphalerite, and galena. Zoning. These deposits often exhibit zoning, with copper-rich zones at the core, transitioning to zinc-rich and then lead-rich zones outward. Structure. They typically occur as lens-shaped bodies that can be several meters thick and extend for several kilometers. Economic importance. Metal resources. Volcanogenic massive sulfide deposits are major sources of base metals, copper, zinc, lead, and precious metals, gold, silver. The polymetallic nature makes them economically significant. Mining and exploration. Techniques such as geophysical surveys, drilling, and geochemical analysis are employed to explore and exploit these deposits. Their value depends on metal content, size, and accessibility. Global distribution. Notable volcanogenic massive sulfide deposit regions include the Canadian Shield, the Iberian Pyrite Belt in Spain and Portugal, and various regions in Australia and Japan. Environmental considerations. Mining impact. The extraction and processing of volcanogenic massive sulfide deposits can lead to environmental issues such as acid mine drainage, which occurs when sulfide minerals are exposed to air and water, producing sulfuric acid. Regulations and mitigation. Modern mining practices and regulations aim to mitigate environmental impacts through waste management, water treatment, and site rehabilitation. Famous volcanogenic massive sulfide deposits. Kidd Creek, Canada, one of the world's largest and richest VMS deposits, known for its high-grade copper and zinc ores. Neves-Corvo, Portugal, notable for its substantial copper and tin resources. Helier, Australia, known for its significant zinc, lead, and silver content. Conclusion. Massive sulfide deposits play a crucial role in the global supply of essential metals. Understanding their formation, characteristics, and economic importance is vital for the mining industry and for developing strategies to manage environmental impacts. Formation of massive sulfide deposits. The formation of massive sulfide deposits, specifically volcanogenic massive sulfide deposits, involves a series of geological processes predominantly associated with volcanic and hydrothermal activities. Here is a detailed overview of how these deposits form. 1. Tectonic setting. Volcanogenic massive sulfide deposits are primarily formed in specific tectonic environments characterized by significant volcanic activity. These settings include mid-ocean ridges, where tectonic plates are diverging, and new oceanic crust is being formed. Back-arc basins, found behind volcanic arcs, where extension occurs due to subduction-related processes. Island arcs, chains of volcanic islands that form above subduction zones. 2. Hydrothermal circulation. The key process in the formation of volcanogenic massive sulfide deposits is hydrothermal circulation, which involves the following steps. A. Seawater infiltration. Crustal permeability. Seawater penetrates the oceanic crust through fractures and porous rocks, driven by the temperature gradient between the cold seawater and the hot magma below. B. Heating and metal leaching. Heat source: magma chambers or volcanic activity beneath the seafloor heat the infiltrated seawater. Chemical reaction: as the water heats up, it reacts with the surrounding rocks, leaching metals such as iron, copper, zinc, and lead. C. Hydrothermal fluids. Enriched solutions: the heated, metal-rich seawater becomes buoyant and starts to rise back towards the seafloor. Hydrothermal vents: these fluids are expelled through hydrothermal vents, often forming black smokers due to the precipitation of metal sulfides. 3. Metal precipitation. As the hydrothermal fluids reach the colder seawater near the seafloor, the rapid temperature drop causes the dissolved metals to precipitate out of solution, forming sulfide minerals. A. Sulphide formation. Primary minerals. Common sulfide minerals include pyrite, chalcopyrite, sphalerite, and galena. Zonation: typically, there is a zonation pattern with copper-rich minerals deposited closest to the vent, followed by zinc and then lead minerals as the fluids disperse. B. Massive sulfide accumulation. Lens-shaped bodies: the precipitated sulfides accumulate to form massive, lens-shaped bodies directly on the seafloor or just below it. Layering: these deposits may show layering due to successive hydrothermal events and varying fluid compositions. 4. Subsequent alteration and enrichment. Post-depositional processes can further modify volcanogenic massive sulfide deposits. A. Metamorphism and reworking. Tectonic activity: ongoing tectonic activity can bury, deform, and metamorphose the deposits, enhancing their complexity and potentially increasing metal grades through remobilization. B. Secondary enrichment. Supergene processes: near-surface weathering can lead to the oxidation of sulfides and the secondary enrichment of metals, particularly copper. 5. Examples and significance. A. Famous volcanogenic massive sulfide deposits. Kidd Creek, Canada, rich in copper and zinc, illustrating the typical structure and metal zonation of volcanogenic massive sulfide deposits. Neves-Corvo, Portugal, known for substantial copper and tin resources. Helier, Australia, contains significant zinc, lead, and silver. B. Economic importance. Metal supply: volcanogenic massive sulfide deposits are major sources of copper, zinc, lead, gold, and silver, crucial for various industrial applications. Exploration: they are targets for mineral exploration due to their rich metal content and relatively predictable geological settings. In summary, the formation of massive sulfide deposits is a complex interplay of tectonic activity, hydrothermal circulation, metal leaching, and precipitation processes, resulting in economically valuable ore bodies. Understanding these processes aids in the exploration and efficient extraction of these essential resources. Properties of massive sulfide deposits. Massive sulfide deposits, specifically volcanogenic massive sulfide deposits, have distinct properties that make them important targets for mining. These properties encompass their physical characteristics, mineralogy, geochemistry, and geophysical attributes. Here's an in-depth look at the properties of massive sulfide deposits. Physical characteristics. Shape and size. Lens-shaped bodies: volcanogenic massive sulfide deposits typically form as lens-shaped or tabular bodies. Thickness: they can range from a few meters to several hundred meters thick. Lateral extent: they can extend laterally for hundreds of meters to a few kilometers. Texture. Massive texture, characterized by a high concentration of sulfide minerals with little to no gangue minerals. Brecciated texture, fractured and cemented by sulfide minerals. Banded or layered texture, resulting from successive episodes of mineral deposition. Mineralogical properties. Primary sulfide minerals. Pyrite, the most common sulfide mineral in volcanogenic massive sulfide deposits. Chalcopyrite, primary copper or mineral. Sphalerite, primary zinc or mineral. Galena, primary lead or mineral. Secondary minerals. Oxides and hydroxides, formed from the weathering of primary sulfides. Supergene enrichment minerals, such as chalcocite, formed from the secondary enrichment processes. Geochemical properties. Metal content. Base metals, high concentrations of copper, zinc, and lead. Precious metals, significant amounts of gold and silver. Trace elements, presence of elements like cadmium, indium, and germanium which can have economic value. Zonation. Proximal to distal zoning, typically, copper-rich core transitioning outward to zinc and lead-rich zones. Vertical zoning, different metal concentrations at different depths, influenced by the temperature and chemistry of the hydrothermal fluids. Geophysical properties. Density and conductivity. High density, due to the high concentration of sulfide minerals, volcanogenic massive sulfide deposits have higher density compared to the surrounding host rocks. Electrical conductivity, high due to the presence of metallic sulfides, making them detectable using geophysical methods like electromagnetic surveys. Magnetic properties. Magnetic susceptibility can vary depending on the concentration of magnetite and other iron-bearing minerals associated with the deposit. Structural properties. Host rock association. Volcanic rocks, often associated with felsic to mafic volcanic rocks. Sedimentary rocks, may be associated with sedimentary layers interbedded with volcanic units. Deformation. Tectonic activity, volcanogenic massive sulfide deposits may be subjected to folding, faulting, and metamorphism, affecting their geometry and accessibility. Alteration properties. Hydrothermal alteration. Alteration zones, distinct alteration zones can develop around volcanogenic massive sulfide deposits, including silicification, sericitization, chloridization, and carbonate alteration. Footwall and hanging wall alteration. Alteration is typically more intense in the footwall, below the deposit, compared to the hanging wall, above the deposit. Economic properties. Metal recovery. Ore grade. High ore grades make volcanogenic massive sulfide deposits economically attractive. Byproducts. The presence of precious metals and trace elements can enhance the economic value. Mining methods. Underground mining, common due to the often steeply dipping nature of the deposits. Open-pit mining, possible for deposits that are near the surface and have sufficient lateral extent. Environmental properties. Environmental impact. Acid mine drainage. Sulfide minerals can produce sulfuric acid when exposed to oxygen and water, leading to environmental issues. Mitigation strategies. Modern mining practices involve measures to prevent and treat acid mine drainage, such as controlled waste management and water treatment systems. Understanding these properties is crucial for the exploration, evaluation, and exploitation of massive sulfide deposits, ensuring that their economic potential is maximized while minimizing environmental impact.